Hello everyone, welcome back to Engineering Escapades, and today I'd like to show you probably the most important circuit that we have. And this is a logic gate, and as you can see it consists of a number of other logic gates. And you can see that when I press one switch, the light turns on, and when I press the other, it also turns on, but when I press both of them, it's off. So you can see it's on, and then I press the other one, it's off. It's on, then it's off. And this might look very confusing, and I agree, it is. It's very confusing. So I've drawn up this very confusing diagram. And also, I am recording this in 50 FPS because it seems the camera has an easier time focusing when the frame rate is a bit higher. I am sacrificing the 4K quality, but it's still full HD, so it should be good. And I'd like you to tell me whether you prefer the 50 FPS or the 25 FPS but 4K. So this diagram is very confusing, but we have three types of gates here. And one is a Nand gate, one is the OR gate, and another is the NOT or Invert gate. And you can see that the Nand gate has two inputs, A and B, and gives the classical NAND output. The OR gate has two inputs, A and B, as well, and gives the classical OR output. The NOT/invert gate is just, it has one input, A, and it returns the inverse of A. So if A is 0, the Q or output is 1. If A is 1, the output is 0. So let's try to identify these circuits. And there are a number of things in this circuit that aren't really necessary, but you might be able to recognize them, even though there is a lot of clutter here. And this circuit is exactly like the one I have here, all the way up to this point, of course, where we take the output and put it into our normal, just standard circuit that turns our LED on that I showed you in the first episode of this series. So, let's have a look. Now, this little piece of circuitry looks kind of like a NAND gate to me. So, we can say that here we have a NAND output. So that is the NAND of A and B. And this, we recognize it's an OR gate. So let's just try to identify these outputs. Now, what about the stuff over here? Now, this looks like another NAND gate. So I'm gonna put a NAND on that, but we don't really know what it is NANDing, but it's a NAND gate. So it's NANDing the outputs of this and this, as you can see, and then the output of that, again, goes into this circuit, which, if we're correct, is just an inverter. So this is the inverse of the NAND gate. But hey, that's just an AND gate. So how can we simplify this diagram? Because we don't care about the resistors. We don't care about the resistor values and all that stuff. And some of you may already know, but we have symbols for this. So if we just go over here and have a look, I have simplified that entire circuit a lot. So this is a NAND gate. This is the symbol that a NAND gate uses. It gives, it has two inputs, A and B, and gives one output, Q. And this is the OR gate. It has two inputs and gives the OR output of those two inputs. Then we have another NAND gate that takes the outputs of both of these gates and it feeds it into this inverter. So, as some of you may already know, and as I've already said, this is just an AND gate. And the symbol for that looks like this. It's very similar to the Nand Gate symbol, but it doesn't have that circle, that tiny circle at the end. And that's really what that circle means. It means invert the output of this standard gate. So we have I've shown you three types of standard gates. There is the AND gate, the OR gate, and the buffer. Then we have the NAND gate, which is just an inverted AND gate. We have the NOR gate, and we have the NOT gate. So before we have a look at this, we will have a look at the tables for these. So the OR gate does this, the AND gate does this. The NOR gate is the exact inverse of the OR gate, as you can see. The NAND gate is the exact inverse of the AND gate, and then we have the buffer and inverter, and both of these only care about the A input. So as you can see, when A is on for the buffer is on, and when A is on for the inverter is off, and then it's the exact inverse. But let's now have a look at this circuit. This circuit so let's see in the case that both A and B are 0. So let's see, this is going to be on. So that's a 1. And the OR gate is going to be off, of course. And the NAND gate, so let's see. This is going to be on unless both of these are on. So they are not, so this is on. But then we invert that and we get a 0. So the output of this circuit right now is a 0. And let's have a look at the other cases. So 0 and 1 on the A and B input. So just to clarify, both of these are A. So this is the A for the, oh, I see that. I'm kind of making it out of focus, but that's A and that's A. And then we have, let me just write that on there, B and B. And if we now have a look and say, so this is a NAND gate, so it's only going to turn off when both inputs are on, which they are not. So this is still on, and this is on, because it's an OR gate. So let's have a look. The NAND gate is then going to say, hey, both of the inputs are on, so I am going to turn off, and the inverter inverts that and turns it on. So our output is 1. So that was 0, and then it was 1. And then let's try the other way around, and that's just going to be exactly the same, because it doesn't really matter which input is what. So let's have a look at the last case, where A and B are both 1. So A and B are both 1 on this NAND gate, so it's going to spit out a 0, and A and B are both 1 on this OR gate, so it's going to spit out a 1, because it spits out whether A or B is on, or both of them. So let's see at this NAND gate. Both inputs are not on, so it's going to be on. The inverter inverts that and gives us a 0. And so we have our table. So that's A and B, and then Q. So you look at this and then you think, what is this useful for? And most of all, since it's a logic gate, it should have its own symbol, which it does. It has this symbol right here, and it looks kind of like an OR gate, but it has this extra thing here. And that extra thing is what makes it different. It's an exclusive OR gate. It's only on when A or B is on, but not both. And why that's really important, I'll get back to that in a second. Then you, of course, have the inverse of that, the XNOR, though I don't really agree with the naming of that, because that would mean it's an exclusive NOR gate, which it's not really. I would rather say it's an N XOR gate, but that's really up to you. And it's not really that confusing, but I still prefer the N XOR, though the standard naming convention is XNOR, so we'll just use that. But let's try to see how this is useful. And to see how this is useful, we first have to learn a thing about numbers. Now, the number 567 in base 10 is 567. But why is it 567? Well, in base 10 we have the ones place, we have the tens place, and we have the hundreds place. Now, what does that mean? It means that the first number, or the last number in, I don't know how you want to look at it, but this 7, let's call it the first number because it's in the ones place. That means we multiply 7 by 1. And in the tens place we have a 6, so that means we multiply that by 10. And then in the hundreds place we have a 5, so we multiply 5 by 100. And when we add all these up, we get the number 567. But as it turns out, there are other number bases, other number systems. One of them is Octal, which is base 8, as the name implies. Octa means 8 in Greek or Latin or something. I think it's Greek. Pretty sure it's Greek. And so, in the octal system, you can see that we still have the ones place, as usual. But every time we move up a place, we multiply by 8 instead of 10. So we can see 8, 64, and 512's place. So let's try to rewrite this 567 to octal. And how we do that is kind of easy, actually. So the first thing we do is we take the number 567, then we look at the largest place, 512. Now, how many times can I add 512 before it exceeds 567? And as it turns out, it's 1. Then we have 512 right now. And then that gives us 55 left over. How many times can I add 64 before it exceeds 55? And that turns out to be 0. Then we do the same for 8, and that turns out to be 6. And then the ones place, we get 7. So some of you may want to say this number is 1067, but that's not entirely correct. Because it's in octal, and our number, or our way of pronouncing or saying numbers, is based on the base 10. So it wouldn't really be correct. You could say it's a 1T0607 or something like that. Just, we can't say that it's 1067 because that's not entirely correct. But as you can see, when we multiply these numbers by their place and add them all up, we get 567 in base 10. Now, of course, these numbers are in base 10, so those are not in the octal system. And the base 10 system, it goes from 0 to 9. And then the octal system, it has numbers from 0 to 7. Now, this is not really important, but it's a way to introduce you to other numbering systems. Now, base 1 would of course be the simplest base you can have, because you have the ones place, and every time you go up a step, you multiply it by 1. So you get the ones place, and the ones place, the ones place. Now, we do actually use base 1 sometimes when you're doing this thing, right? So you do 1, 2, 3, 4, and then 5. So this is just a way of keeping tabs on 5s, really. And you could call it a base 5 system, or something like that. I'm not entirely sure, but that it's still base 1, really, I would call it. And some of you are probably familiar with this way of counting when you do things like, I really can't come up with an example right now, but you're probably familiar with this way of counting on paper. But it's not really that interesting. So, what if we add just one more number? What if we had 0 and 1? So base 2. Well, we then get the 1's place, the 2's place, the 4's place, and the 8's place. And here you can see I've written up a few numbers in base 2. I have 5 and 6. So let's add 5 and 6 in a couple of different bases. So 5 and 6 in base 10 add up to 11. But hey, that doesn't fit into one place. That exceeds 9. And it exceeds 9 by exactly... or it exceeds 10 by exactly 1. So we'll write 1. And then we will do what's called carrying. We'll carry a 10 over to the 10's place. And we get 11. So this is the base 10 representation of it. Let's do it in octal. Okay, let's see. 5 plus 6 is 11, but that exceeds 8, right? So how much does it exceed 8 by? Well, that's 3, and then we'll have 1. So that is the number 11 in octal. So that's, you can't really call it 13, it's 1, 3, let's call it that. And just to be stupid, let's add them up in base 1 as well. So here I have the number 5 in base 1. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Now, how do we add numbers in base 1? Well, it's very, very easy. You just append them to the end. It's kind of like putting apples together. So, Tom has 5 apples. Tom gets 5 more. So you just append them to the end here, and you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But let's get over to the interesting part. How do we add numbers in base 2? Well, let's have a look. We do it exactly the same way we would do other numbers. So 1 plus 0, that does not exceed, that's not more than 2, right? So, or it's not more than 1. So we get a 1. And 0 plus 1 is 1. And then 1 plus 1, that's 2. But that's more than we can write in a single place. So how do we do that? Well, we do exactly the same as before. We see that, hey, we put a 0 here, and then we carry over, and then we get a 1 here as well. So that's really all there is to it. That's how you add in any numbering system. Now, let's get back to why the XOR gate is so useful. So let's see here. The XOR gate gives us a way of figuring out the sum, the sum right here. So if the input is 1, if the input is 1 and 0, we have a 1. And if it's 0 and 1, we get a 1. But if it's both on or both off, we get a 0. So that's why the XOR gate is so useful. It allows us to add two numbers together, two binary numbers. And then how do we calculate the carry? Well, the carry is only on, in this case, when both of these are on, right? So the carry goes, but hey, that's an AND gate. So let's just write those up. I've got them written out here, and as it turns out, this is what's called a half adder. And why is it a half adder? Well, it is a half adder because we have a problem with this. And the problem is that it only deals with two numbers. It deals with A and then B, and let's see, A and B as well. And it's a half adder because the output of this is a sum and a carry. So this would be the sum and this would be the carry, right? And this works fine for one number, but sometimes you deal with a carry. And what if the numbers look like this? What if what you're adding looks like this? Well, then you'd first add these, that's a 0, but hey, I have another one I need to deal with, so that's a 1, and I still have a carry, so I carry out as well. So this is a half adder because it's a half. And how do you make a full adder? Well, how do you make a full? You add two halves. So let me just write that up. So I've now drawn out this entire circuit, and I've rearranged the components a bit, but it's still the same thing. It's an XOR gate in parallel with an AND gate, so the A and B inputs both go to these. But then we have another half adder right here, and they're also both in parallel. But we take the carry input into both of the gates, and then we take the first sum into both of the gates as well. And what we get at the end here is our sum and then our carry out. So how would you then do this? Well, you'd align all of these in parallel, and then you'd take the carry out like this into the next carry in of the next full adder. And what you'd get then is a circuit that adds numbers. And that's really cool, to be honest. That's a circuit that can take a series of on or off inputs and then make them another series of on or off inputs that in base 2 represent a number that is the sum of both the inputs. And that's really cool, I think. So that was just a quick introduction to this XOR gate, and also a very, very quick introduction to number systems and how binary addition works, base 2 addition. And I hope you enjoyed this. I know this video was a bit longer than usual, but I hope it wasn't too long, and I hope you'll subscribe. I hope you liked the video. Comment what you'd like to see next, and I'll see you guys next time.